Hello students, welcome to Maths Online Academy by Sandhya, myself Sandhya. Today topic is Chapter 1, Real Numbers, Theorem 1.4. So, yesterday we discussed Theorem 1.3. Today is 1.4. Let's see the statement. Let x equal to p by q be a rational number such that the prime factorization of q is of the form 2 power n 5 power m, where n comma m are non-negative integers, then x has a decimal expansion which terminates. So we have to show p by q is a rational number. Let x be x is a rational number, and that is in the form of p by q, and the q is in prime factorization, and that is in the form of 2 power n 5 power m, and n comma m are non-negative integers. X has a decimal expansion. So for that, let's say one example. For example, for x, here x equal to p by q is in the form na. Here we take 3 by 25. For taking example 3 by 25, and we have to show that is rational number, so and so and so on, everything. So 3 by 25. This is in the form of p by q. That is such that the prime factorization of q is in the form of 2 power n 5 power n. Here q is equal to 25. So do the factorization. 5 5s. So you can write 5 square 5 into 5. Okay na? So 5 into 5 means 5 square. For 2 power 0. Here 2 power 0 equal to 1 into 1. In 1 place we are writing 2 power 0. For any one, 3 power 0 equal to 1. For power equal to 0 is 1. Here we want to show 2 power n 5 power n. That's why we are writing 2 power 0. So is in this 2 power 0 into 5 power 2 is in the form of 2 power n into 5 power m. Yes? Is 25 is in the form of 2 power n and 5 power m. Here n comma m are non-negative integers. See, that implies n equal to 0, m equal to 2. These two are non-negative integers. This one also proved. Then x has a decimal expansion which terminates. Decimal expansion, let's see. For 3 by 25, decimal expansion means 3 divided by 25. 0. Yes? 25 ones are 25. And again here 5. You can write 0. 25 twos are 50. Here became 0. Remainder became 0 means that decimal expansion is terminated. Decimal expansion equal to what? You can write 3 by 25 equal to 0.12. This is the decimal expansion, that is it terminates. The decimal number ends with the finite number, that is called terminate decimal numbers. So x equal to p by q is a rational number. We are taking let x equal to p by q is a rational number. For example, we are taking 3 by 2, 3 by 25. So 3 by 25 is in the form of P by Q, such that factorization of Q. Here what is the Q? 25. Factorization is 5. You can write 5 square. 2 power 0 means 1. 2 power n, 5 power m. Here values are n equal to 0, m equal to 2. 0, 2 are non-negative integers. Non-negative integers. Up to this one finished. Where n, are non-negative. X has a decimal expansion. So 3 by 25. 3 divides by 25 na? So 0. 25 ones are 25. Remaining is 5. Again 0. 25 twos are 50. Remainder is 0. So the answer is 0.12. So 3 by 25 you can write 0 in decimal numbers 0.12. This is terminate decimal number. The theorem is proved by using we are taking here one example. So for taking one example, we proved that x equal to p by q be a rational number such that factorization q is in the form of this, and n, m are non-negative integers, and x has a decimal expansion which terminates this number. Okay, hence proved. Hence proved. And next theorem is 1.5. Next theorem is 1.5. We discuss that one. And next theorem is theorem 1.5. Before going to the theorem, let we discuss what are non-terminating recurring decimals. In this theorem, we discuss about non-terminating recurring decimals. For example, we take 1 by 3. So, if you divide this one, 3, 0.0. 3 3 is a 9. Again 1. So, again 0. 3 3 is a 9. Again 1. Again 9 and 1. So, it's continuing. Remainder become 1 and it will go 0.33333. So, the answer of 1 by 3 equal to 0.333. The decimal number of 1 by 3 equal to 0.3333. So, it's not finite. It's continuing. 3 is continuing here. So, not ending. This type of rational numbers are called non-terminating recurring decimal numbers. And one more example. For example, 5 by 11. See, here also you divide 5 and 11. 0.0. 11 4s are 44. And again here 6. So 0. 5 is a 55. And here answer is 5. Again 0. Means 11 4s are 44. Again 6. 0. 5 is a 55. Again 5. So here 0.454545, it's continuing. It's not ending. It's repeating. So that type of rational numbers are called non-terminating recurring decimal numbers. So you got it. What are terminating recurring numbers? Non-terminating recurring numbers. Decimal numbers. Okay. This type of rational numbers are called non-terminating recurring decimal numbers. So you can write these rational numbers into non-terminating recurring decimal forms. These are called non-terminating recurring decimals. Based on this, we prove theorem 1.5. So let's see. Theorem 1.5. What is the statement? Let x equal to p by q be a rational number such that the prime factorization of q is not of the form of 2 power n 5 power n, where n comma m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring numbers. So that number is in the form of, that expansion is non-terminating, repeating numbers. So for example, for that, let's see one example. Before we discussed what are non-terminating recurring decimals. In that we took 1 by 3 and 5 by 11. So here also same take. X equal to p by q be a rational number. Here for example we are taking 1 by 3. A rational number such that the prime factorization of q is not in the form of, so here q equal to 3 and we have to prove q not equal to in the form of 2 power n and 5 power n. If you do the factorization of q 3, what will you get? 1 into 3 same, so 3 power n. Here that q is in the form of 2 power n 5 power m. We can't write 3 in the form of 2 power n 5 power n. So this is not equal to in the form of 2 power n 5 power m. So this is the rational number such that the prime factorization of q is not in the form of 2 power n 5 power n. We are writing 1 into 3. So 3 power n. You can't write 2 power n into 5 power n. So that is not satisfying. And where n comma m are non-negative integers. So then x has a decimal expansion. So we have to prove decimal expansion. Here let's we do division 0.08. Again here coming 0. So 3 is the 9. Again 1 remainder. Again you take the 0. 3 is the 9 and again 1. So it's repeating. It's not ending. It will continue 3. So 1 by 3 equal to 0.333 and so on. So that decimal expansion is non-terminating, repeating decimal numbers. Before we discussed what are non-terminating, repeating or recurring numbers means, the division or the decimal numbers are not ending. Those are repeating. So this is in the form of non-terminating, repeating decimals. So hence proved by using, we took one example using of this 1 by 3. We proved this is in the form of p by q and q equal to not in the form of 2 power n and 5 power m, and that decimal form is non-terminating, repeating decimals. So hence proved. Before we discussed theorem 1.3, 1.4, 1.5. By using this, you can do these problems in page number 11. Page number 11. In page number 11, you do these problems. You can do these problems. If you solve the, if you know the division, you can solve all this, do these problems in page number 11. So In next, solve the exercise 1.3 and 1.4 in next video. If you like this video, please share and subscribe. Thank you.